In one of the previous videos, we said that elimination can take place under two conditions. One is a stepwise reaction mechanism. The other one is concerted. We've already talked about concerted mechanisms. That's the E2 reaction. In this video, we'll talk about stepwise elimination reactions, otherwise known as the E1 reaction, which takes place by a stepwise mechanism to give alkenes. Okay, so in a generic E1 reaction, you'll have a substrate. Let's say it was, just to make it more specific, let's say it was tertiary butyl bromide. What would happen would be the leaving group would leave first. So the first step is loss of a leaving group to generate a carbocation. But unlike the SN1 reaction, instead of a nucleophile attacking the carbocation, what happens instead is that the reagent acts as a base to abstract the proton to generate the alkene product that you see here. Because this step is slow and rate determining, just like in the SN1 reaction, the rate is only going to depend on the concentration of your electrophile or your substrate. It's not going to depend on the concentration of your base, right? So we can increase or decrease the base concentration without affecting the rate. Okay, so let's do an E1 reaction mechanism for this compound. The first step, as I mentioned, is loss of a leaving group, which will generate the tertiary carbocation, right? And then it's helpful to draw in the CH bond that's going to be lost to give our alkene shown here in the product. So in the next step, ethanol, instead of acting as a nucleophile, it will act as a base, and it's important to draw in this lone pair of electrons. This is going to transfer a proton from this compound to ethanol, and these two electrons will become the pi bond. So another product of this reaction would be protonated ethanol, which you could show if you'd like or not. So there's only two steps here. One is the leaving group leaving. The second one is a proton transfer to give us our elimination product. Okay, so how does substitution of the substrate affect the reaction? Well, this is very similar to an SN1 reaction. Since the rate determining step is formation of the carbocation, as we increase the substitution of our alkyl halide as we go from primary to secondary or tertiary, the rate of E1 reaction will increase, right? And that's because the rate determining step in each one of these reactions is the leaving group leaving. And so when this leaving group leaves, we generate the most stable tertiary carbocation. When this leaving group leaves, we generate a secondary carbocation. And when this leaving group leaves, we generate a primary carbocation, which is the least stable. So there's a highest activation energy barrier for generation of this primary carbocation, which means it will happen slowly. And for all practical purposes, it won't happen at all. Okay, so there is a huge amount of similarity between the SN1 and the E1 reaction. The first step is exactly the same. The leaving group leaves to generate a carbocation, but this is where the two reaction pathways diverge. So in the presence of any decent nucleophile, in the presence of any good or even poor nucleophile, then the major pathway will be the SN1 pathway. The only time that we'll see this pathway compete, the only time we'll see E1 compete, is if we have just a horrible nucleophile, something that can't function as a nucleophile at all. The only thing it will be able to do is act as a base. So usually we're going to get mixtures of SN1 and E1 reactions. In almost all cases, SN1 will be the major pathway. We'll talk about those cases where E1 is the major pathway in a second. So the only time that you're going to see E1 as the major pathway is if you start with an alcohol starting material and a strong acid that has a non-nucleophilic counterion. The only examples are going to be sulfuric acid and phosphoric acid. Any other strong acid is going to have a nucleophilic counterion. For example, let's say we treated this alcohol with HCl. Well, then we would observe an SN1 reaction, right? Because the counterion is Cl-, which is a good nucleophile, right? HBr is another example where we would see an SN1 reaction because the counterion is Br minus. So remember, the mechanism is that we protonate the alcohol, turns that into a good leaving group, and then it leaves to generate a tertiary carbocation, right? It's much more likely that if this is a good nucleophile, that the SN1 reaction pathway will outcompete. So the only way we can influence the E1 reaction to be predominant is if we use an acid such as sulfuric acid or phosphoric acid, and then the counterion here looks like this. It's extremely stable because this negative charge on the oxygen has 3 resonance structures that are equally contributing. So this, we're going to say, is not a nucleophile. So the only thing it can do is act as a base, and so the E1 reaction will compete in this case. So only when these two strong acids are used will we see E1 reaction as the major pathway. Otherwise, like in these cases, the SN1 pathway will be major. So what if we can form multiple products? For example, you have in this particular case, you have this set of beta hydrogens is the same as this set of beta hydrogens, which would give the less substituted alkene, or you could form the more substituted alkene. Remember, what we're doing in the intermediate here, after protonation, several steps, we get a tertiary carbocation. So if we lose these hydrogens, we form this alkene. If we lose these hydrogens, we form this alkene. The E1 reaction, unlike the E2 reaction, will always favor the most stable or the most substituted alkene. The reason is because this reaction is reversible, so we can protonate this alkene to reform the carbocation. And so for thermodynamic reasons, we're going to funnel the reaction mixture down to the most stable, their lowest energy product. Okay, so let's say we had this particular example, right? What you want to look at is you want to first identify your beta hydrogens. You have 2 beta hydrogens here, and you have 2 beta hydrogens here. Notice if we eliminate this way or this way, that we'll get the same product, which would be 2-pentene. But remember, you can form cis-2-pentene or trans-2-pentene, right? So you're going to have 2 products. This one is going to be the major product, which is what the question is asking. We'll also form a small amount of a minor product, which is the cis isomer. But if we're asked for the major product, this one is going to be the major product. It doesn't matter if we eliminate this way or this way, it would be the same. And as you can see, when we run the reaction, 75% of the mixture is the cis product, 75% is a trans product, 25% is the cis product. Okay. So finally, remember, if a carbocation intermediate is generated in the reaction, you can see carbocation rearrangements. And a good red flag for this is that, see, here you have 3 methyl groups attached to this carbon. Now you only have 2. 1 methyl group migrated over. Remember, the only time that you'll see carbocation rearrangement is if you form a secondary carbocation next to a carbon that's prone to rearrangement, either a tertiary carbon or a quaternary carbon. So let's write out the mechanism for this reaction. The first step is protonation of the alcohol by sulfuric acid. I think it's helpful to write out the entire formula here so we can show the lone pair of electrons forming a bond to hydrogen, and these electrons becoming a lone pair on oxygen. That will give us this OH now is OH2+. So when it leaves, it will be stable. It'll be a water molecule. So now this bond breaks. We have a leaving group, leaving step. We get this carbocation. It's a secondary carbocation, which is next to a quaternary carbon. So this is likely to undergo rearrangement. One of our methyl groups will move over, which will lead to a new, more stable tertiary carbocation. Okay? Now, in the last step, the base that we generated in this step will abstract the proton to regenerate the sulfuric acid catalyst. So these two electrons become our alkene, and we get this product of carbocation rearrangement. Okay, so to summarize, the E1 reaction is called E1 because elimination, and it's unimolecular, meaning the kinetics only depend on the concentration of our substrate, the thing that's bonded to the leaving group. The only time that E1 is the major reaction pathway is when you start with a secondary or a tertiary alcohol and you add a strong acid with a non-nucleophilic counterion. The E1 will always accompany other SN1 reactions, but it will be the minor pathway, and so in those cases, I'm not going to ask you to worry about it. I'm usually or always going to ask you to identify the major reaction or the major reaction pathway.